As far as sensory input goes, cameras offer an incredible amount of data. From obstacle detection to facial recognition, automated systems can extrapolate a ton of information about their environments from images. One problematic side effect of capturing images is barrel distortion. Barrel distortion is the phenomena by which pixels farther from the center of the image are pulled closer to the center point. This distorts the image to look as though it's being wrapped around a barrel. While this may be desired for some photography, this effect distorts the actual shape of the world, and in robotics, an accurate representation of objects in the world is necessary for navigation. It's easy to see here that the ends of the wall appear farther away from the middle, and that the water bottle bows to the right. Correcting this distortion is somewhat trivial. As you could imagine, pixels farther away from the image center are simply pushed even farther away, effectively flattening the image. Picking the perfect amount of distortion correction, however, is difficult. This is because a small change in the correction offers an imperceptibly small improvement in the image, as you can see here. This is where automating the process becomes important. For automation, we need an image with objects at known intervals from each other. We created this specific pattern so that every object is the same known distance from the copies around it. This makes it easier to associate pixels with a physical piece of paper in the real world. Our automation is a four-step process. Firstly, we perform an image processing technique called blob detection to pick out the bottoms of the triangles. Secondly, we create homography, which is a method for projecting image pixels to corresponding positions in the real world. This essentially is a measure for how close the image is to the real-world object positions. The benefit of the homography is that it compensates for the camera not being directly in line with the image. Next, we push the known points through the homography to get the reference points to the bottoms of the triangles. Lastly, we iterate over all the points, adding up the differences between the reference points and the actual points. Here is a demonstration of our algorithm automatically finding the best distortion correction. As we move through the different distortion adjustment values, it's easy to see the image flatten out. At this point, the error begins to get worse, meaning that we've found the best value. With a perfectly undistorted image, we can now calculate exact object positions in the real world.